Okay, chain rule. Chain rule, what is it for? Okay, it is for this kind of situation. What for, right? It is for functions that are in composition. Okay, for functions, say f function composite g function. Okay, and we take a derivative of the result. So we can recognize the compositive function. So that we're taking derivative of this composition. Okay, recall, right? We have learned how to differentiate derivative of sum, which is the sum of derivative. So derivative of sum is the sum of derivative. Sum of derivative. The derivative of difference is the difference of derivative. So we have learned these. And we have also learned product rule, right? So if we differentiate two functions that are multiplying each other, all of these rules, sometime after we cover the same rule, you will realize we can apply all of them. So today we're only gonna on this video we only talk about chain rule. Okay, so what chain rule is for in comparison with the other situation, which is in the case of product, right? F of x multiply the derivative of g of x plus g of x multiply the derivative of f of x. And of course, we have a quotient rule. So let me write it down so you know that there's a distinction. Okay, but as the question gets more complicated, we may need to use all of them. May need to use all of them. So one function divided by another function. So in these cases, okay, in the addition case, so subtraction case, multiplication case, we actually cannot use chain. Chain rule is for composition of two functions. Okay, so let me just quickly type the derivative of quotient squared. Okay, and on the top is g of x, the denominator, multiply the derivative of f acting f of x, which was the numerator, multiply the derivative of g. So that's the quotient rule. So now let's look at derivative of chain rule. Okay, derivative of chain rule basically says, okay, hold on, let me make some more space here. Okay, so it is look like this: the derivative of f of g of x. So we have two layers. Okay, so how do we find derivative of f of g of x? Take an example. Okay, I know you can find that formula in the book. The formula says f prime, okay, f prime g of x multiply g prime. What does that mean? Okay, so this is the formula. This is the official formula. I'm going to give you some examples. Okay, examples. The first one, for example, we have, we simply have x squared, right? the derivative of x squared is 2x, right? But if we differentiate, instead of differentiating x squared, we're differentiating something else squared. And this something else is going to be 2x plus 1. I'm going to differentiating 2x plus 1 squared. So when we have a 2x plus 1 squared, and of course we know that you can differentiate it other way, but if we differentiate it with the chain rule, we're going to see 2x plus 1 squared as the composition of two functions. Okay, so let me write it down. Is seen as composition of two functions. And what are these two functions? One of the function is f. Well, okay, f of x, which is equals to x squared. And the other function, we see it as g of x equals to 2x plus 1. So if we composite these two functions, right? So if you check and composite f of g of x, we are going to get f of g of x. Okay, follow the rule of composition. And then we're going to have f of g of x is 2x plus 1. So g of x is substituted by 2x plus 1. And now we're going to apply the rule of f, which is squaring the input. The input here in this case is 2x plus 1. So we get 2x plus 1 squared. You see, that's the composition. That's the composition. Now, according to chain rule, when we differentiating this function, we see it as differentiating the composition with 2. So what we do is that we have f, we know the f, and we know the g, right? We know f, we know g. So we checked, it does make the composition. So what's the derivative of f? So the derivative of f is 2x. And what is the derivative of g? The derivative of g, okay, dx is, we differentiate 2x, the derivative of 2x is, of course, it's 2, the derivative of 1 is 0. Okay, so I'm actually going to put this on the side. I'm going to put this on the side. Okay, so this is just verifying. Verify. Okay, verify it's indeed the right composition. Okay, now once we have identified f and g, and we also know their derivative. But one more thing I'd like to point out, you can see f is a very simple function, and g is also a very simple function. In fact, both of them are polynomials, so we know how to find the derivative of the polynomial. So now when we come back, find the derivative of 2x plus 1 squared, and we're going to take the 2x, right? 2x is a derivative, okay, of x squared. But now we have 2x plus 1 squared. So we take the 2x, and you think of, hold on, let me put this on the side. You think of this as, okay, let me just put it this way, see if you get it. Okay, so it's just 2x, x, now is the derivative of x squared is 2x. The derivative of parentheses squared is 2 times the parentheses. If that is clear. Okay, you let me know. So the derivative of x squared is 2 times parentheses. The derivative of x squared is 2x. The derivative of 2x squared is 2 times the parentheses. Multiply, it's not over. Multiply the derivative of g. Okay, so we differentiate the parentheses. And it is, so in the end, we get 4 times 2x plus 1. Of course, you can FOIL it if you want. Okay, so now, that's how we differentiate by chain rule. Okay, so let's look at another example. So this is example 1. Let's look at example. Let's look at another example. Okay, example number 2. I'm going to differentiate. I'm going to differentiate derivative of cosine squared. Oops. Cosine squared. Okay. Cosine squared is seen as a composition of 2 functions. Okay, the first one, okay, so we talked about that cosine x, cosine squared x is actually the same as that, cosine squared x. So these two are the same. These two are the same. So when we differentiate this function, we see it as a composition of 2. Okay, so cosine square x, which is the same as cosine square x. Okay, it's just written slightly differently, but they mean the same thing, is seen as a composition of the following 2 functions. And what are they? One of it is f of x equals to x squared. And the other function is g. G is, of course, cosine x. So once again, we're going to differentiate f. Okay, so we're going to differentiate f, which we have done that, right? That's 2x. And we're also going to differentiate g. The derivative of g, which is cosine x, is negative sine x. And now we're going to put things together. When we put things together, we're differentiating this piece. Okay, so what we do is that we're first going to differentiate. You're going to see it as something squared. Okay, so this is parentheses squared. That's how you see it. Parentheses squared. It equals to 2 times parentheses. Parentheses squared. It's 2 times the parentheses. So it's going to be 2 times cosine x. Okay, we apply this rule to cosine square x, and then multiply the derivative of cosine x, which is negative sine x. And in the end, we get negative 2 sine x multiply cosine x. You can write cosine x times sine x as well. Okay, so let's look at another example. Okay, this other example, we've been using x squared multiple times, right? We've been using x squared multiple times. So let's look at something else. Suppose I want to differentiate this piece, okay? X to the power 3 plus 2x minus 1 to the power of 9. To the power of 9. How do I differentiate this function? Well, once again, this function is seen as a composition. Okay, this function is seen as a composition of two other functions. And what are these other functions? One of them is f of x equals to x raised to the power of 9. And the other function, d, which is going to be the entirety of the parentheses. All right, now, when we differentiate this parentheses raised to the power of 9, okay, we are going to apply the rules the same way. So we're going to differentiate. So we know the derivative, right? The derivative of f right, which is x raised to the power of 9, is equal to 9 multiply x raised to the power of 8. So when this piece is applied to the composition, we're going to get a 9 multiply the parentheses raised to the power of 8. Okay, you see this parentheses raised to the power of 9, so the parentheses to the power of 8 when we apply this rule in the chain rule setting. And of course, what's inside the parentheses? And we know what's inside the parentheses. We put it right here. And this is not done. We have to differentiate what's inside the parentheses. What's inside the parentheses? Derivative of what's inside the parentheses, which is the derivative of g of x, is going to be, we differentiate x raised to the power of 3, that's going to be 3 x squared. And the derivative of 2x, of course, is going to be 2. The derivative of -1 is going to be 0. So applying chain rule, the first part, we apply to the derivative of f, substitute it by, whatever is in the parentheses, and then 3x squared. The next question is, how do you show your work? How do you show work? How do you show work? Well, when you show work, actually, you only have to show this part of example number 1. For the second example, you only have to show, you can even omit this part. Okay, this part is optional. You just show this line, that will be sufficient. On example number 3, you don't have to show all of these actually. You just have to show that part. I hope that's clear. Okay, so let me put it together. How to show work. Okay, how to show work on example number 1, 2, 3. So I'm going to give you a clear answer. How to show work on example number 1, 2, 3. On number one, okay, the only work you have to show is just this much. That's it, you're done. On number 2, okay, the only part of work you have to show is this much. You're done. Okay, on number 3, what do you have to show? Just this much. You're finished. You're finished. So to show work for example 1, 2, 3, that's how you can show your work. Okay. Let me see if I should give you another example. Okay, let me see. I'm gonna probably just get one more example because I don't want to make this too long. I was just thinking of another example because some of those questions can be seen done differently. Okay, this example I'm going to show you is something I thought of as I was driving home. Okay, I thought this example is simple and direct. to illustrate, sometimes you can have multiple ways to do it. For example, example number 4, right? Example number 4. Suppose I want to differentiate to the power e to the power of 2x, e to the power 2x. Okay, very commonly seen situation. But if you look at e to the power 2x, this function can be seen in 2 different ways, okay, because of power rule. It can be seen as e to the power x, then to the power 2, okay? But in this case, the composition would be f of x would be what? Would be x squared. And g of x, right? G of x is e to the power x. So that's one way to composite. But there's another way to composite. Okay, so before we get to the other way to composite, right? So in this case, if you see it as such, when we differentiate this function, you would differentiate it the following way. Okay, you differentiate it as e to the power x squared. Okay, so you differentiate as such. So you first differentiate x squared, which you're gonna get 2 times e to the power x, right? Multiply e to the power x, e to the power x. The derivative of e to the power x, of course, is still e to the power x. In the end, you're gonna get 2 times e to the power of 2x, because you add the exponent x plus x. Now, that's one way to differentiate, because you look at it, you look at the composition in that manner. But e to the power 2x can also be seen as another composition. It can be seen as e to the power of 2x, in which case my f is going to be e to the power x. Okay, my g is 2x. In this case, when so this is the composition. This is the composition. So I see the composition made a different way. But are we going to get different results? Let's watch. Okay, so we're going to differentiate this, right? So first we're going to differentiate e to the power something, e to the power x. The derivative of e to the power x is e to the power x. So we get e to the power 2x here, because the derivative of e to the power something is e to the power something with respect to the same something. Multiply the derivative of 2x is 2. So in the end, we get the same answer. Well, we should get the same answer, even though we look at it from different perspectives. So there are situations like that. Okay, so let's look at one more question with chain rule. Okay. I think all the other examples will have to let's look at there's this one question which is in your homework is e to the power of tangent theta. Okay, and of course we're going to differentiate with respect to theta. Okay, so how do we see this composition? This composition is very obvious. Okay, this composition is completely obvious, which is e to the power x for f for the outer function, and tangent theta is for the other function. So when we differentiate, we just differentiate e to the power x, which is going to be e to the power of whatever tangent theta. And then we're going to differentiate tangent theta, right? And tangent theta is derivative of tangent theta is secant squared theta. And we're done. We're finished. Okay. In our next video, I will be talking about chain rule and product, quotient, even addition, subtraction. Thank you for watching. Wait, doesn't turn off. Okay.